The first thing to recognize is that if you put a positive test particle there, you know, the Q2, by the way, Q2 is negative, right? So Q2 is gonna attract this, and Q1 is gonna repel. But because of the distances, there is no way electric field is zero here. You know, the electric field is KQ over R squared. And there's no way it's here, zero here, because they attract each other. So it has to be here somewhere, okay, on the left-hand side. That's first thing to recognize. So if you put a positive charge there, so Q1 is gonna repel, and Q2 is gonna attract, and there is a way they can balance each other. So let's write that out. So F1 will be equal to F2 at that X point. So F1 is K 1.4 times 10 to the negative 8. By the way, the picture shows negative 8 and your writing shows negative 5. So I went with negative 8 from the picture. X squared, and then K times 1.8 times negative 10 to negative 8. It's not going to matter here because it's going to go away. But I took that for the entire problem. So technically we have quadratic equation here, okay? Like this. And then bring everything to one side, make this positive, so you will have 0.544x minus 0.0436 equal to 0. So this one produces two answers, okay? The first one is negative 0.08, the other one is 1.34. These are all meters. Now this can't happen because that means that you're somewhere here, and we already decided it's not there. So this is your answer, okay? That's where the E is 0. On the, if you want, like on the negative side, so left hand side, or you can call x equals negative 1.3 meters. According to the origin, actually you should write that, because according to the origin it's negative. Now for the B part, now we have Q3 here, so Q1, Q3, they're gonna repel each other because they're both positive, and Q2, Q3, they're gonna attract each other, okay? And we're gonna have to find the resultant force. So F12 is K 1.4 10 to the negative 8 times 4.2 10 to the negative 8 divided by 0.24 squared. So I would recommend calculating these numbers. 7.56 10 to the negative 9 Newton, okay? And you know K is 9 10 to the 9. Okay, now F23 is K 1.8 10 to the negative 8 times 4.2 10 to the negative 8 over the hypotenuse, which is 0.24 square plus 0.18 square, square rooted, and then square again. So it takes care of each other, which is oh, I wrote this wrong. So this is 7.59 Newton, and this one is 9.137 or 8, 10 to the negative 9 Newton, okay? Now, you know, we have F12 this way, F23 this way. That means we need to divide this f23 into two parts with this theta. So total fy's will be f12 minus the y component of f23. All you have to do is 9.138 times 10 to the negative 9 minus 7.56 10 to the negative 9 times cosine of theta there, which is actually, you can write it like this. Cosine of theta is, no, I'm sorry, sine of theta. Sine of theta is 0.24 divided by the hypotenuse, which already we have up there. So from here, you will get 3.114 times to the negative 9 Newton. And the x component of this is just f23x, which is same idea, times sine theta, cosine theta, sine is here, and that is 4.54 10 to the negative 9. This problem was like 5, really. So the total electromagnetic force, electrostatic force is Fy, total Fy squared plus total Fx squared, which is right here, 3.14 times 10 to the negative 9 squared plus 4.54 times 10 to the negative 9 square rooted, and you get yourself the answer 5.5 10 to the negative 9 Newton. And the angle is this angle. So this is where Q1 is, this is where Q3 is. So the angle is, if you do it like that, I calculated this angle, which is arctangent of F total Y over F total X. And that angle is 34.7 degrees. If you're looking for that one, that is 55.3. Okay, I wasn't sure what kind of or which direction, but this is the magnitude, and this angle could be one direction. It can be adjustable. If you're looking for this one, 180 minus that. Okay, but the direction is like somewhere like this direction. I don't know. I think it can be I think explained that way. Okay, long problem. I guess worth my time, I hope. Anyway, bye bye.